the original motivation for this is to introduce this scale factor. What is the original physical motivation?
What's the original physical motivation? Is I think if you're approaching a phase transition or a critical point, then you can start getting excitations at all scales and all wavelengths. And so the description was to say that your theory will develop some sort of a scale invariance near a phase transition. And without relativistic invariance, in sort of honest materials or something like that, then you might have some scaling, which is some Lipschitz scaling of this nature. So time scales, so the momentum scales in a certain way, energy scales in a possibly different manner.
I noticed that on other side of the scale, for example, when z equal to 1/2, for example, you assume z greater than 1.
I did assume z greater than 1.
If z is 1/2, for example, you will get something like confinement in the effective potential. That would be quite interesting.
Yes, I'm glad you noticed that. So first of all, the scaling over here is motivated by sort of phase transitions and behavior near a phase transition. But absolutely, if you go back to this potential over here, for z less than 1, it can turn up over here. You get confinement or bound states or something like that. Now, it turns out that from a holographic point of view, or from a sort of a book point of view, if you actually ask, is it physical to have z less than 1, you find out in order to create sort of a Lipschitz background, the background geometry, well, you would have to use matter fields to violate the null energy condition. And so you might have some problems. It depends on how much weight, how much emphasis you want to give to energy conditions in general relativity. But let me just say that it does seem to have some problems with the energy conditions to have z less than 1.
I see, but that problem may not be real because once the z is smaller than 1, you have a very peculiar property which people never studied before. You have a confinement property in this effective potential, and you don't have a free propagation wave. There are many new properties came out in that case. I thought it's quite interesting. I hope you do something about it.
Well, thank you. No, I think it is interesting to consider cases. I agree.
Okay, any other question? So you don't have a Lorentz invariant meaning for the energy, right? So high energy means what in some specific system like laboratory system or center of mass system?
I guess I'd say some are mass system. You still have time translation invariance. They can still define energy. But there would be something like a center of mass or some sort of reference to the frame. And then you're measuring energy with respect to that.
Please.
Hi. In your last slides, I saw the C theorem in the future directory.
Possible C theorem, yes.
Yeah, so I'm just a bit wondering, so if you have a non-relativistic theory on the boundary, basically you can define the energy and the momentum differently, and does that mean that you have two central charge?
I don't know the answer to that.
Because usually when you basically take the central charge as the coefficient of the energy momentum tensor, right? But now in the non-relativistic case, basically energy and momentum are two different things. So
that's right.
Should I expect that you have two central charges in that case?
You might possibly expect more than two even.
Oh, right, and then cross.
But let me think, even in the relativistic case, I can also, I might call it central charge. I can also think about some of these charges as viral anomaly coefficients.
Oh, sure.
And so in 4 dimensions, you have C and A, for example.
Oh, yeah, sure. But for P theorem, you have 1, right?
Yeah, you have an A theorem or something like that. But
exactly.
I agree. But the point is, even in the relativistic case, there might be more than one quantity.
I agree.
That's interesting. So it's not unique to the non-relativistic case. They might have more than one type of central charge. If you try to write out, I don't remember, there's several groups that looked at it a little bit. They talk about Lifshitz scale anomalies. If you try to write out some sort of scaling transformation or scaling algebra and ask if there's any anomalies that can develop, I think in 4 dimensions there's 2 possible anomalies in the scale invariant theory. Sorry, in this Lifshitz type theory. One of them in the standard field theories turns out to be, I don't understand the details, I think just 0 or trivial right offhand. And then there's one type of potentially central charge, which I don't know if I should call it central charge. It's some scale anomaly coefficient. So there's one obvious quantity in 4 dimensions at least. Oh, sorry, not 4 dimensions. In 2 plus 1 dimensions, z equals 2. The scaling anomalies also depend on z to get just the right balance between energy scaling and momentum scaling. So you have combinations of E with k squared or something like that, which only shows up for z equals 2.
Okay, and about anomalies, is those like scale anomaly somehow have the similar properties as a relativistic theory, like appearing only in odd dimension, something like that, or not?
Not necessarily.
Okay.
Yeah, in the relativistic theory, it's sort of an even dimension sort of case. Here, I said 3-dimensional theory with z equals 2 has this type of scaling anomaly, but the z equals 2 almost fakes an extra dimension. So 3 dimensions with z equals 2, in some of the scaling properties, feels a little bit like a 4-dimensional theory. It's a fake 4 dimensions, but that's to sort of motivate that you can get sort of a scaling, Lifshitz scaling anomaly in 3 dimensions, in an odd dimensional theory.
So you're saying it's basically z dependent.
So it's z dependent,
okay.
And that's one of the obnoxious features of that. Having said that, let me just mention one other thing, is from a bulk point of view, or solving Einstein's equations point of view, you can still ask, what does the null energy condition impose on these Lifshitz-like metrics? And I already mentioned one thing is you want z greater than or equal to 1 to satisfy the null energy condition. So some of these holographic C theorems are proven through the null energy condition. And so you can show something like z bigger than or equal to 1 at a scaling fixed point comes from null energy condition. You can ask if you can define C functions from a holographic point of view, irregardless of the lower dimensional field theory interpretation. You can define these functions that are monotonic, just because the null energy condition gives you an inequality. The problem is, if you ask whether those sort of holographic functions or have any physical meaning or not, the answer is not so clear, because they don't sort of go to constants at fixed points. And so you have functions at fixed points which are bigger than other functions at fixed points, but you don't really know what the functions are supposed to mean in the first place. But I've been curious about that. I don't have any good answers. And I think it would be interesting if someone could figure out whether there are these C-type theorems for the non-relativistic case.
All right. Yeah, thanks.
Okay, then let's thank Professor Liu again. So let's go to the next talk.